We are in Chapter 11, Infinite Sequences and Series, Part 3. Section 11.10 is titled Taylor and Mclaren Series. One type of power series is the Taylor or Mclaren series. So we have a theorem, and our theorem says if f has a power series representation expansion at A, that is, if f of x equals the sum from n equals 0 to infinity of c sub n times x minus a to the nth power, where we have the absolute value of x minus a is less than r, then its coefficients are given by the formula c sub n is equal to f to the nth, and that's a derivative. So n being 0 would be just our normal function. If n is 1, that's going to be the first derivative. N is 2, that's the second derivative, and so on. Evaluated at a and then divided by n factorial. The next thing we have is a Taylor series, and the Taylor series of the function f at a is f of x equals the sum from n equals 0 to infinity of c sub n times x minus a to the nth power, or using up above what c sub n is, we have the sum from n equals 0 to infinity of f to the nth derivative of a divided by n factorial times x minus a to the nth power. Expanding this out, we have first n is 0, so we have f, our function evaluated at a, divided by 0 factorial, which is just 1, times x minus a to the 0 power. Then we have the first derivative evaluated at a divided by 1 factorial times x minus a to the first, plus second derivative of f evaluated at a divided by 2 factorial times x minus a squared, plus the third derivative of our function evaluated at a divided by 3 factorial times x minus a to the third, and this would continue on. A special case is when we have a is equal to 0, then our Taylor series becomes what's called a Mclaren series, and we have f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 divided by n factorial times x to the n, and again this is when a is equal to 0 in a special case of our Taylor series. And so expanding this out, we have f evaluated at 0 divided by 0 factorial times x to 0, plus the first derivative evaluated at 0 divided by 1 factorial times x to the first, plus the second derivative evaluated at 0 divided by 2 factorial times x squared, plus the third derivative evaluated at 0 divided by 3 factorial times x cubed, and then so on. And so we have the sum of the first n plus 1 terms of the Taylor series is the Taylor polynomial. And the Taylor polynomial is denoted t sub n of x. T sub 0 of x is equal to f of a. T sub 1 of x is equal to f of a plus f prime of a times x minus a. And if you note, this is exactly what we saw back in Calculus 1 to finding a tangent line. And so the first order Taylor polynomial is just that approximation that we use to find a tangent line at x equals a. And then t sub 2 of x is equal to f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus a squared. And then to find t sub 3 of x, or our third order Taylor polynomial, we can find the third term and add that third term on, which is the third derivative evaluated at a divided by 3 factorial times x minus a to the third. And so these are able to approximate a function at a. And so if we have a function that is difficult to approximate, we would be able to keep adding on these derivatives evaluated at a divided by that value factorial times x minus a to that power. And that gives us a better approximation out to so many decimal places, and we'll see that momentarily. And so right below it, it does say, notice that the first order Taylor polynomial is just a linear approximation of the tangent line. And so we saw this back in Calc 1. And then Taylor series polynomials match the function perfectly at the center x equals a. They lose accuracy as we move from the center. They gain accuracy as we add more terms to the polynomial. So the Taylor series represents functions exactly. So the example on the next page says find the Mclaren series for f of x using the definition of a Mclaren series. Also find the associated radius of convergence. So the first thing to remember is that these Mclaren series are going to be centered at 0. And so what that means is that our a value is equal to 0. And so the function that we have for part A equals ln of 1 plus x. And since we're finding a Mclaren series, we can rewrite this as the sum from n equals 0 to infinity of f to the nth derivative evaluated at 0 divided by n factorial times x to the nth power. I'm going to set up a table to organize our numbers and our derivatives evaluated at 0. The table is a good way to keep everything organized. And so our function that we have is f of x equals ln of 1 plus x. And so we're going to have our first n value is going to be 0. And then I will go out just to kind of see to 5, and I'll put dot dot dot. If I need to, I can write out some more terms. Usually having so many, you can see that pattern that is going on and be able to rewrite it as a series. And then I have my derivative, and then I have to take my derivative and evaluate it at 0. And so our function that we have when there is no derivative is the natural log of 1 plus x. And then evaluating this at 0, we would have ln of 1 plus 0, or ln of 1, which is just 0. So taking the derivative of ln of 1 plus x, first derivative, we would have 1 plus x to the negative first, or 1 over 1 plus x, and then rewriting it since we have to keep taking derivatives. And so the next derivative, the second derivative that we have, I need to use that chain rule. And so negative 1 out in front, and then we end up with 1 plus x to the negative second times the derivative, the inside is just 1. And then likewise, continuing this process down, we have negative 2 times negative 1 out in front would be positive 2 times 1 plus x to the negative third times the derivative of the inside, which is just 1. And then our fourth derivative is going to be negative 3 times 2 is negative 6 times 1 plus x to the negative fourth times the derivative of the inside is 1. Then negative 4 times negative 6 is 24 times 1 plus x to the negative fifth times the derivative of the inside, which is just 1. And so then evaluating these, and the first one that we have is evaluating this at 0. First derivative would just be 1 plus 0 to the negative first, which would be 1. The next value that we have would work out to being negative 1. The next value that we have would be 2 times 1 to the negative third, or just 2. Likewise, we would get negative 6 for the fourth derivative evaluated at 0. And then the last one, we would have 24. And again, these would continue on the same process. So now taking what we have, so expanding this, our first term is going to be 0 over 0 factorial times x to the 0, plus our next term is going to be 1 over 1 factorial x to the first, plus the third term that we have is negative 1 over 2 factorial x to the second, plus the next term we have is going to be 2 over 3 factorial x to the third, plus the next term would be negative 6 over 4 factorial x to the 4th. And then the next term we would have would be 24 over 5 factorial x to the 5th, and then dot dot dot. This would continue on. So simplifying this, the first term that we have would just be 0. So I'm not even going to write that down. The next term would work out to be an x. The next one's going to be negative 1/2 x squared. And then the next term is going to simplify to 1/3. And to see that, you can write this out. And we have 2 over 3 factorial, which is 3 times 2 times 1, or 1/3. So plus 1/3 x cubed. Likewise, expanding out 4 factorial, we have negative 6 over 4 times 3 times 2 times 1, and the 6 and the 3 times 2 would reduce down to 1, and so we'd be left over with negative 1/4 x to the 4th. Likewise, we can do the same thing with 24 divided by 5 factorial and get plus 1/5 x to the 5th plus dot dot dot, and this would continue on. And so now we need to rewrite this as a Mclaren series. This is going to go from n equals something, and we'll put that in a moment, to infinity. And what I notice here, and if you wanted to, you can add in a 1 over 1 and x to the first. And so this is going to be x to the power of n. And I'm going to start in at 1 since that's my first exponent. So I will put x to the nth on here. And then I notice that it's alternating. So I need to have a negative 1 to a power. And if you were to put an n on here, you would notice that that first power would be negative, and our first term is not negative. So I'm going to say n minus 1. And then it's divided by the same value that you have as your exponent, or n. And so this would be our Mclaren series. The directions do also ask to find the associated radius of convergence, as listed up above. And so in order to do that, I'm going to use the ratio test. And with using the ratio test, we were looking at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And so for this problem, we have the limit as n approaches infinity of a sub n plus 1. And the negative 1 to the n minus 1 power isn't going to matter since we are dealing with absolute values. So we have x to the n plus 1 over n plus 1. And rather than dividing by a sub n, I'm going to multiply by the reciprocal of it, which is going to be n over x to the n. And so then this would simplify, and if you notice, you're going to have your x's will reduce down and you just end up with one of them left over. And so then this simplifies to, and if you notice, the limit is as n approaches infinity, and so the x that we have left over can come out in front of the limit, but in absolute values. So the absolute value of x times the limit as n approaches infinity of, and we have n over n plus 1. And so to deal with this, I'm going to multiply both the top and the bottom by 1 over n, and the reason why is because right now if I were to evaluate the limit, it's indeterminate and it's infinity over infinity. So multiplying both top and bottom by 1 over n, this is going to simplify to the absolute value of x times the limit as n approaches infinity of, and we are going to have 1 over 1 plus 1 over n, which this would go to 0. And so this limit is going to converge to 1. And so we have the absolute value of x times 1, or just the absolute value of x, is less than 1. And so we can see that our radius of convergence is going to be equal to 1. and that interval would go from -1 to +1. Part B, right below this, we will circle, and we'll try this one together in class. The example at the top of the next page says find the Taylor series for f of x centered at the given value of a. Also find the associated radius of convergence. So very similar to what we did last time, however this time we have a Taylor series, and it's not centered at 0, it's centered at -3. So we need to write out our Taylor series, and so we know that this is going to be equal to the sum from n equals 0 to infinity of, and it's going to be the nth derivative evaluated at a divided by n factorial times, and it's x minus a raised to the nth power. And so since we know that a is equal to -3, I'm going to go ahead and substitute that in. And so we have the sum from n equals 0 to infinity of the nth derivative evaluated at -3 divided by n factorial times x minus -3, or x plus 3 to the nth power. And I'm going to set up a table just like we did in the last example. And n always starts at 0, since that's just our original function, which is going to be 1 over x, but I'm going to rewrite it as x to the negative first. And so this is to find our nth derivative, and again the first one at 0 would just be the original function, and then we need to evaluate this at -3. So, and again we can add more to these to kind of see that pattern to write down that Taylor series. So I'm going to go ahead and find the first derivative of my function, which is x to the negative first, or 1 over x. And this is going to work out to be -x to the negative second. The next one would be 2x to the negative third. Then we have -6x to the negative fourth, and then 24x to the negative fifth. And then for each of these, we have to evaluate what the derivative is at -3. And so the first one that we have would be -3 to the negative first. Then we have -3 to the negative second, 2 times -3 to the negative third, -6 times -3 to the negative fourth, and then 24 -3 to the negative fifth. And again, these would both continue on, especially if we need more terms. And sometimes you do need more terms just to kind of see that pattern. So let's go ahead and write these out. So for the first term, I'm going to have -3 to the negative first over 0 factorial times x plus 3 to the 0 power plus, and then the next derivative that we have, or the first derivative that we have, would be -3 to the negative second over 1 factorial times x minus 3 to the first. And then the next term is going to be 2 times -3 to the negative third divided by 2 factorial times x plus 3 to the second plus the next term we have is -6 times -3 to the negative fourth all over 3 factorial times x plus 3 to the third plus, we have 24 -3 to the negative fifth all over 4 factorial times x plus 3 to the fourth, and this would continue on. And so simplifying these, the first term that we have is going to simplify to just being -1/3. And that's because x plus 3 to the 0 would just be 1, and 0 factorial is also 1. And so -3 to the negative first is going to be 1 over -3, or -1/3. The next term we have is going to be a negative, and it works out to be -3 to the negative second over 1 factorial, and 1 factorial is just 1. And so the 3 would actually move to the denominator and would stay 3 squared. And we have x plus 3. In the next term, we have a 2 in the numerator and a 2 factorial, which is just 2 in the denominator. So that would reduce out. And so for this, we have negative 3 to the negative third, which is going to be a negative value also. And I'm going to write it as 1 over 3 to the third. And then x plus 3 to the second. The next term that we have is negative 6 over 3 factorial. And 3 factorial is equal to 6, so I will cancel those out. I have a negative sign left over, and then I have negative 3 to the negative fourth, which would become a positive 3. And so I'm going to rewrite this as 1 over 3 to the fourth times x plus 3 to the third. The next term that we have is 24 divided by 4 factorial. 4 factorial is 4 times 3, which is 12, times 2, which is 24, times 1, which is 24, and so those would reduce out. And negative 3 to the negative fifth would be a negative value, and I'm going to rewrite as 1 over 3 to the fifth. And then we have x plus 3 to the fourth, and then I'll put some dots in there because this does continue on. And so let's see if we can rewrite this as a Taylor series. And so for my Taylor series, I'm going to say from n equals 0 to infinity. And what I notice is that everything is negative, and every single term does have an x plus 3 in it. The first one, it would be to the 0 power, so I do notice that they all have an x plus 3 to the nth power. And I'm going to put a negative out in front because all of them are negative. And what I notice in the denominator is that I have 3 raised to a power, and this first one that I have is to the first, and so that's 1 more than that starting value of 0. And so for this, I'm going to say to the n plus 1. And you can always check this by first substituting in n is 0, then n is 1, n is 2, and so on. And so this is our Taylor series for our function, which is 1 over x, centered at negative 3. And then to figure out it says also to find the associated radius of convergence. So to figure this out, I'm going to use the ratio test again, which is the limit as n approaches infinity of the absolute value of, and this is going to be a to the n plus 1. And so for this, we would have negative x plus 3 to the n plus 1 over 3 to the n plus 1 plus 1, or n plus 2, times, and then I'll multiply by the reciprocal of a sub n, which is going to be 3 to the n plus 1 over negative x plus 3 to the n. And so if you notice here, we do end up with an extra 3 in the denominator. And then likewise, we end up with an extra x plus 3 in the numerator. And so this is going to simplify to the limit as n approaches infinity of the absolute value of, and again, the negatives don't matter because we are in absolute value, x plus 3 over 3. So this would all just be the absolute value of x plus 3 over 3 times the limit as n approaches infinity of, and technically it would just be 1. And we know that this limit of a constant would just also be equal to 1, and this needs to be less than 1. So we have the absolute value of x plus 3 over 3 has to be less than 1, or the absolute value of x plus 3 is less than 3, or that our radius of convergence is equal to 3. We have one more example right below this that I will go ahead and circle, and we'll try f of x equals sine of x to write a Taylor series centered at pi over 2 in class together. At the top of the next page, we have important Mclaren series and their radii of convergence. I'm going to give this box a star and say we need to know these for the upcoming exam. And so we have different functions here. First one we have is 1 over 1 minus x, and this is equivalent to the sum from n equals 0 to infinity of x to the n. And then it's also expanded out, and the radii of convergence is 1. The next one that we have, the next function is e to the x, which is equivalent to the sum from n equals 0 of x to the n over n factorial. And then we have sine and cosine, and sine and cosine are similar, except for you'll notice that with sine it is negative 1 n x to the 2n plus 1 divided by 2n plus 1 factorial, and this is the sum from n equals 0 to infinity. And cosine is very similar to that, however, it is the sum from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. Both of those are expanded out there. In addition, we also have the tangent inverse of x, which is the sum from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1, and that's also written there. And note that the radius of convergence is 1 for this problem. For e to the x, sine x, and cosine x, the radius of convergence is infinity. The next one that we talk about here, the function is ln, so the natural log of 1 plus x. This is the sum from n equals 1 to infinity of negative 1 to the n minus 1 times x to the n over n. The last one that we have is 1 plus x raised to a kth power. And so this is going to be the sum from n equals 0 to infinity of k, choose n elements, x to the n. And this is also written out here so you can see. So first example that we have says, find the Mclaren polynomial of degree 8 for cosine x squared. So it wants a Mclaren polynomial. And so we know that cosine of x from the table up above is equal to the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n all over 2n factorial. So then for the problem, which for us is cosine of x squared, we're going to have the sum from n equals 0 to infinity of negative 1 to the nth. And then instead of an x, we actually have an x squared. And so I will write x squared to the 2n all over 2n factorial. And this would simplify to the sum from n equals 0 to infinity of negative 1 to the nth power times x to the, and multiplying your exponents together, we have 4n all over 2n factorial. And so expanding this out and looking for degree 8, the first term that we have, substituting in 0, that's going to work out to being just 1. The next term that we have when n is 1 is going to be a negative, and we have x to the 4th over 2 factorial, or just 2. This is degree 4, and we're looking for degree 8. So the next term we plug in is when n is equal to 2 for our third term. And so we would have a positive value, and then we're going to have x to the 4 times 2, or x to the 8th, over, and then we would have 2 times 2 factorial, or 4 factorial. And so this would simplify to 1 minus x to the 4th over 2 plus x to the 8th over 24. The next example says, find the Mclaren polynomial of degree 5 for x e to the negative x. So the first thing that we know is that e to the negative x would be equal to the sum from n equals 0 to infinity of, and instead of x raised to the nth power, I'm going to put negative x raised to the nth power over n factorial. But you'll notice also that we have an x times e to the negative x. So I'll put that x out in front of my summation. And so from here we have x times, and then evaluating this and expanding it out. First term that we have, substituting 0, you would get 1. The next term that we have is going to be negative x to the first over 1 factorial. And then we have negative x to the second all over 2 factorial. And then negative x to the third over 3 factorial. And then this continues on. And so again, we are looking for degree 5. So distributing through the x and simplifying this a little bit, we would have x minus x squared over 1 plus x to the third over 2 minus x to the fourth over 3 factorial, which is 6, plus, and then the next term would have been negative x to the fourth, and that would be positive times x would be x to the fifth, all over 4 factorial, which is 24, and this is of degree 5. The example at the top of the next page, I'm going to go ahead and circle, and we'll work on this one together in class. The next example says use the Mclaren series for e to the x to calculate 1 over the 10th root of e correct to 5 decimal places. And so for this problem, we're going to first look at that Mclaren series for e to the x, which is going to be e to the x equals, and it's the sum from n equals 0 to infinity of x to the n over n factorial. And this is asking for us to calculate 1 over the 10th root of e, which for this problem, this would be the same thing as e to the negative 1/10 power. And so e to the negative 1/10 power is going to be approximated by the sum from n equals 0 to infinity, and x for this case is negative 1 over 10 to the nth power all over n factorial. And then expanding this out, we would have, so first term we would just have 1 minus the second term, since it is a negative 1/10 to the first, would be negative 1/10, plus the next term is going to be negative 1/10 squared over 2, plus the next term is negative 1/10 to the third over 3 factorial. And I'll put a factorial in that 2 also, which works out to being just 2. Plus the next one would be negative 1/10 to the fourth all over 4 factorial, plus, and then this continues on. So we have 1 minus 0.10 plus, and then negative 1/10 squared divided by 2 would be plus 0.005. And as of right now, it says correct 5 decimal places, so you'll see that that first term is 1, and then the next term is affecting that first decimal place, and then the third term is affecting the third decimal place. So we have to go out to where it's not affecting any more of those numbers out to the 5th decimal place. So the next term that we have would be minus, and 1/10 to the third divided by 6 is 0.0001667. And so this is still affecting the 5th decimal place. And then the next term that we have would be plus, and 1/10 to the fourth divided by 24 is going to be 0. And then 0.00004. And so you'll notice that that is no longer affecting the decimal place that we would have. And so this would equal 0.90484. And we'll say down here that the next term, and you can always calculate it to see it exactly, doesn't affect fifth decimal place. And so a little note, you can actually evaluate with your calculator e to the negative 1/10 power. And substituting this in on your calculator and writing out 5 decimal places, we get 0.90484. And so that does check. So this was a good approximation for the function 1 over the 10th root of e. So the example right below it says use a series to evaluate the limit. And so for this problem we have the limit as, and what we're going to do here is notice that if you were to evaluate this at 0, you would have indeterminate. And we talked about using different rules back in Calculus 1. So one of them was L'Hopital's rule, which would work for this since it is indeterminate. But let's try this another way, and let's try to use the sequences and series that are discussed in Chapter 11. So the numerator is sine x, and if you go back and look at your Mclaren series, you'll notice that expanding this out, you have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and this keeps continuing on. And the denominator is just x. And so from here, you can divide each of these terms by that x that's in the denominator, and we get the limit as x approaches 0 of, so the first term would be 1, minus, and then x cubed over x would be x squared over 3 factorial, plus x to the 4th over 5 factorial, minus x to 6 over 7 factorial, and then this would also continue on. Since we're taking the limit as x approaches 0, these terms would all, and all the consecutive ones too, would all be going to 0. So the limit as x approaches 0 of sine x over x would just be equal to 1. And again, another method that we talked about to evaluate this limit would be L'Hopital's. So you can definitely go back and try that to check to see that it matches. The problem continues on to the next page, and this one says find the limit of e to the x minus e to the negative x, and I'm going to go ahead and circle this one, and we'll work on this one together in class. The next example says find the sum of the series, and this one is the sum from n equals 0 to infinity of 3 to the nth over 5n times n factorial. And so I'm going to go ahead, and I notice that I have 3 to the nth and 5 to the nth, so I'm going to rewrite this as the sum from n equals 0 to infinity of 3/5 to the nth power times 1 over n factorial. And then this is going to be the same as the sum from n equals 0 to infinity of 3 over 5 to the nth power all over n factorial. And what we notice with this, if you go back and look at the Mclaren series that we have, that e to the x is very similarly written, except for it's x to the n over n factorial in the sum from n equals 0 to infinity. So for this, we would have e to the x, but our x in this problem is 3/5. And again, note this is from the table that we have on the previous page, and this is the sum from n equals 0 to infinity of x to the n over n factorial is equal to e to the x. The next example says use the Mclaren series to find the integral of x squared ln of 1 plus x dx. And I'll circle that one, and we'll look at that one together in class. The last example that we have says use the series to approximate the definite integral within the indicated accuracy. So for this problem, it wants us to estimate the integral from 0 to 1 of sine x to the fourth dx, correct to 4 decimal places. So in order to do this, we know that we would have the integral of sine x to the fourth dx, which we are unable to integrate. U sub wouldn't work. Integration by parts would take some time. So this is another method to do to approximate this. And so we have the integral from 0 to 1 of, and I'm going to go ahead and look at the table that we have for Mclaren series. Find sine of x, and every time you see an x, we're going to put an x to the fourth, since that's what we have that we're taking sine of. So x to the fourth cubed over 3 factorial plus x to the fourth to the fifth over 5 factorial plus x to the fourth to the seventh over 7 factorial plus x to the fourth to the ninth over 9 factorial, and again this continues on dx. And so simplifying this, we would have the integral from 0 to 1 of, and it's x to the fourth minus, and this is going to now be x to the fourth raised to the third is x to the 12th over 3 factorial plus x to the 20th over 5 factorial minus x to the 28th over 7 factorial plus x to the 36 over 9 factorial, and again this continues on dx. And so integrating this, since we have x's raised to powers, we would just be able to use that power rule by adding 1 to the exponent and dividing by that same value. And so the first one that we have would be 1/5 x to the fifth minus, and then adding 1 to this exponent, we're going to have x to the 13th, and multiplying by in the front, we would have 13, 1 over 13 times 3 factorial, plus the next term is raised to the 20th power, so adding 1 to that, we have x to the 21st, 1 over 21 times, and it's 5 factorial, minus x to the 28th, we're going to add 1 to it, and we have 1 over 29 times 7 factorial, and then this last term that we would have that I have written, and again this continues on forever, adding 1 to our exponent, we get 37, so x to the 37th times 1 over 37 times 9 factorial. And again, this continues on, but we're evaluating this whole thing since this is a definite integral from 0 to 1. So substituting in 1s for all the x's, we would get numerical values, but substituting in 0, we would just have 0. So this is going to be 1/5 minus 1 over, and it's 13 times 3 factorial, plus 1 over 21 times 5 factorial, minus 1 over 29 times 7 factorial, plus 1 over 37 times 9 factorial, and again this continues on. And this wants the series to be correct to 4 decimal places. So let's look at these as decimal. 1/5 is going to be 0.2. Minus 1 over 13 times 3 factorial is 0.01282, plus 1 over 21 times 5 factorial is going to be 0.00040. The next term that we have is minus 0.00001. And then the next term that we have would be plus 0.0000007. And if you notice, This last term is affecting decimal places that are farther away from the fourth decimal place that we need. So this is correct to 4 decimal places and not needed. And so adding up these 4 terms that we have, we get 0.18757, or we can also say correct to 4 decimal places as 0.1876. And so therefore we can say the integral from 0 to 1 of sine x to the 4th dx is approximately equal to 0.1876.